In this video, we're going to talk about section 2.2, which deals with density curves and normal distributions. Density curves, we're going to talk about the two measures of center and how they're affected by skewed distributions and then a symmetric distribution. We're also going to define them in terms of different types of points. And then we're going to talk about normal distribution, specifically the empirical rule, and then how to find certain proportions of data underneath the curve given a certain range of z-scores or actual raw scores from a story problem. Let's start with density curves. You're going to be able to estimate the relative locations of median and mean on a density curve. A density curve is a mathematical model for a distribution. It is an idealized description giving a compact picture of the overall pattern of the distribution, ignoring minor irregularities and outliers. So don't imagine a bar graph or a histogram where you have a bunch of jagged edges. The curve is going to be smooth. It's more going to be something more like something we see from an algebra class on a xy plane. It is always above or on the x-axis and has an area of 1 underneath it. Because all density curves have the same area of 1 underneath it, if you were to change the spread, it's going to change the height of the curve. So I've drawn two examples of that over here. On the right side, if you push it together, the curve kind of jumps up at you, and then if you kind of spread it out or stretch it, left and right, it becomes a lot shorter. And that's because the area must be constant for any density curve. Now the mean and median are defined a little bit differently with density curves. The median is called the equal areas point because if the area under the entire curve is 1, that means the median is going to be the exact moment where it cuts it into 0.5, 0.5 on each side of the median. Now the mean is called the balance point, so if you were to take your curve and actually make it out of a piece of wood and try and balance it at a certain point, the mean would be that exact point where it would balance. This set of diagrams shows you how the skewness or symmetric, symmetric data sets actually affect the measures of center. In a skewed left distribution on the left side of the diagram, we have the mode at the very top of the graph, the most frequent point, and A and B are both pulled to the left of the distribution due to the skewness. Now, the one that's pulled the furthest is the mean. The mean is highly affected by outliers and skewness, so that's the furthest pulled. Median is affected by outliers and skewness, but not as much as the mean is. It's the exact mirror image with skewed right. You have A being the mode at the tallest point of the curve, and then B and C, median and mean respectively, C being closest to the skewed side of the curve because the mean is the most affected measure of center for skewness. The last picture is a symmetric curve. This is more like a normal distribution we're going to talk about in a couple minutes. The mode, median, and mean all lie on the point A. B and C are just going to be random numbers in this curve. Every measure of center lines up for a symmetric curve in the middle there. You're going to be able to use the empirical rule on this page. It's also called the 68, 95, and 99.7 rule. You're going to use it to estimate areas or proportions of values in a normal distribution. We already talked about how the area under a curve for density curve is always 1. And we're going to be able to find a proportion of that entire curve of 1 in a normal distribution using the empirical rule. Normal curves and normal distributions, they are symmetric, single-peaked, and bell-shaped. You also may have heard this called a bell curve. Normal curves are describing normal distributions. The word normal is capitalized regardless of where it occurs in a sentence. That is because it is a proper noun. So this normal should be capitalized right there. Normal distributions are special, so we give them a special name. The mean and median, we talked about before, are in the center of the curve. A normal distribution is specified by two numbers, most importantly, the mean and the standard deviation, sigma, so mu and sigma. You need to have that for every normal distribution you're talking about within a problem. Now, onto the empirical rule, or the 68, 95, and 99.7 rule. 68% of the data falls within one standard deviation of the mean. That works for any normal distribution. And in this diagram here, I found these two pieces at 34% apiece. I get the 34% by taking 68% within one standard deviation above and below. And since it's symmetric, I simply cut the number in half. 34 and 34 make 68. The next two sections within 2 standard deviations of the mean comes from this second statement. 95% of the data falls within 2 standard deviations of the mean. So from 1 standard deviation to 2 standard deviations, we jump up 27%. Now 95% of the data lies within this 2 standard deviation range. Where I got 13.5% from is that we have 27% extra in that orange section. 27% divided over 2 areas, cut it in half, is 13.5%. The last statement, 99.7% of data falls within 3 standard deviations of the mean, and that's where I get the 2.35% from. The jump from 95% to 99.7% is 4.7%. You cut that in half, this number right here, and you get 2.35% on each side. Now you'll notice that after within 3 standard deviations, you only have 0.3% of unaccounted for outside that range. That's not a lot of data. It's actually, in most cases, a negligible amount of data. We don't really worry ourselves with that. So if you deal with a standard deviation much higher than 3 on either side of the mean, you're talking about a very small probability of it happening. Normal distributions are used quite a bit, so we developed a shorthand for it. It's capital N followed by 2 numbers inside of parentheses. The first number will be mu, your mean, and your second number will be sigma, your standard deviation. So if you're going to write a shorthand with a normal distribution with a mean of 430 and a standard deviation of 32, it would look like this. And let's pretend we have a normal distribution given to us, and it has a standard deviation of 10, a mean of 50. So let's just say, for example, I wanted to figure out how much data falls between 40 and 60. Well, this should be easy. It's 50 plus 10 and 50 minus 10. And that's within 1 standard deviation. I know that 68% of the data falls between these 2 numbers. And that works out great if you have whole number standard deviation scores above and below the mean. The problem is, in this case, we want to know the proportion of values between 45 and 73. Neither one of those numbers are a whole number of standard deviations away from 50. So this is what we're going to do. We're going to take these raw scores and change them into z-scores or standardized scores. So instead of seeing the raw scores underneath, you're going to see these standardized z-scores. Because normal distributions are all shaped the same, this distribution can represent any set of data. And this is the part of the standardization of Belk or normal distributions. They can be used for any set of data that's normally distributed. Now, our next couple of I can statements, it says you can use table A or technology. In this video, we're strictly going to use table A. The first part asks you or tells you you're going to find the proportion of z values in a specified interval or a z-score from a percentile in the standard normal distribution. That is strictly math term talk, so z-scores and proportion of z-values. The second I can statement talks about the proportion of values in a specified interval or the value that corresponds to a given percentile in any normal distribution. The second I can statement refers to contextual numbers. So in terms of the examples we're going to talk about in a second, we're talking about typists and words per minute numbers. And that's going to be your second I can statement. We're going to be ending those problems in terms of concluding with a sentence that contextualizes the number that we find. Table A is going to be our number 1 tool for these types of problems. It's actually in the back of your book. I'm going to show it to you right now. This table you'll find in the back of your book in the table section, page T1 and page T2. The first page deals with the negative z values. You'll notice them on the left side of your your table. It goes all the way up to negative 3.49, which is 3.5 standard deviations below the mean, and you'll notice that 0.0002, very, very small area under the curve. And it goes all the way up to 3.49, which is 0.998. And it shouldn't be surprising that if you were to add 0.0002 and 0.9998, it's going to add up to 1, hence giving our area of 1 underneath the curve. You'll notice that the z-scores on the left side, I'll go to the tenths, and then across the top you have the hundredths place, 0.00, 0.01, 0.02, all the way up to 0.09. You're going to take your z-score to the nearest tenths place, go to the nearest hundredths place, and then meet them in the middle of the table. So let's just make up a z-score. For example, I'm going to say I have a z-score of negative 1.94. Here's how you do that. Find negative 1.9 in your table right here. Find 0.04 up top, and then you're going to meet in the middle. What you're going to find is 0.0262. What does that number mean? That number means to the left of that z-score, there is 2.62% of the data, or that's the proportion of the values in the data set to the left of that. And you know it's to the left because if you look at the diagram on the top of this paper, it shows you right here, table entry Z, and then it has the left side shaded. That's showcasing to you that every proportion listed here in the table is to the left of the z-score. Let's go back to our examples now. Let's start with just an example, z equals 1 from the table. Let's go back to our table. Go to the positive side of the table. 1.00, you're going to go to 1.0, 0.00, meet in the middle here, and it's 0.8413. I'm going to transfer that number back to our notes. So it's a portion of 0.8413 or 84.13%. Let's think about the empirical rule and can make a connection here. If I draw a normal curve, put mu in the middle, let's make one standard deviation on each side. We know for a fact that within one standard deviation, there's 68%, so it's 34% on each side. We also know that the entire curve has an area of 1 or 100%, so all the way to the left up to the mean is 50%, and we just defined up to one standard deviation is 34%. That means your total all the way up to one standard deviation is 84%, which matches this number we found from the table. Now, obviously, the table is a lot more accurate. It has the nearest 10,000ths of a proportion, but it displays the empirical rule perfectly. Now, we're going to go over examples actually how to use Table A within the context of a problem. If you follow these steps within these types of problems, it's going to make your life a lot easier. If you skip any part of these steps and thinking that it's too easy to do a certain simple step, it could cost you the problem, maybe getting it wrong when you easily could have gotten it right by following these simple steps. So example 1, suppose that the distribution of net typing rate in words per minute, or WPM, for experienced typists can be approximated by a normal curve with a mean of 60 words per minute and a standard deviation of 15 words per minute. What is the proportion of typists that type fewer than 50 words per minute? We're going to draw a picture and shade the appropriate area. This is the one that students frequently skip, thinking that it's too easy to do. I always encourage students to do this because it gives you a nice visual of what's going on here and what you need to look for. So in the middle goes your mean. In this case, it's 60. And to find the other standard deviations, you're going to either add or subtract 15. So if you're going to the right, you're going to add 15. To the left, subtract 15, because that's your standard deviation. So at one standard deviation, 75. 2 is 90. 3, 105. To the left, you're going to have 45, 30, 15. And we're now going to shade. So I'm going to change the color of my highlighter. We're going to shade the appropriate area. And if I may, I'm going to draw in where 50 goes, because that's our number here. 50 is going to be right there somewhere. So when I highlight it, the area of that portion of the curve, which is good because it's kind of how our table A is set up, everything to the left of a certain z value. State the problems in terms of x. We're looking for x less than 50. Now, in order to use the table, we can't use this number 50. There's no 50 on the table, but there are z-scores, so we're going to take this x value and convert it to a z-score so we can use the table A. So z is going to be equal to, remember it's your x value minus your mean, which in this case is going to be mu, divided by your standard deviation, or sigma. So this is going to be 50 minus 60 divided by 15. It's approximately negative 0.67. So let's find that exact z-score on our table. Let's go to our table. Negative 0.67. So negative 0.6. So find that right here. Negative 0.6. 0.07 is on this column. We're going to go all the way down till they meet right here. 0.2514. That's our proportion of data to the left of that z-score. 0.2514 or 25.14%. Now, if you're talking about strictly z-scores and nothing else, there's no story problem behind this, you could leave it as 25.14% and you're answering the question. But we're talking about an actual problem with units and a context. So we're going to draw a conclusion using a complete sentence. So something as simple as this. Approximately 25.14% of typists type slower than 50 words per minute. Slower, fewer could work there too. But this simple sentence, just to draw a conclusion, helps to conclude the problem as a whole and also ties in the context of the problem as well. So that type of problem, we're just going to the left of a z-score. It's pretty straightforward. You just find the z-score from the table A and you convert it to a percentage and then you write your sentence. The next problem. Suppose that the distribution of net typing rate in words per minute, WPM, for experienced typists can be approximated by a normal curve with a mean of 60 words per minute and a standard deviation of 15 words per minute. What is the proportion of typists between 45 and 90 words per minute? This is a different question right now. It's no longer asking just to the left of a number. We want in between 45 and 90 words per minute. So first thing you should do is draw a picture. So draw your curve. Put your mean in the middle, 60. Draw your standard deviations, 75, 90, 105, 45, 30, 15. So we're going to shade the appropriate area. So that's in between 45 and 90. Now, this looks different than before. Our table is not set up to find the proportion between two data values, so we're going to have to use some mathematical operations to help us out. State the problems of x. State the problem in terms of x, so 45 less than x less than 90. You're going to find the z-scores for the corresponding values. If you go ahead and calculate for each, 45 minus 60 over 15, you'll find out exactly -1. This one, 90 minus 60 divided by 15 is going to be exactly 2. So this turns into -1 less than z less than 2. Now, we're going to use table A to determine proportion. I'm going to try and show you how it's going to work though with two diagrams. So I'm going to draw two normal curves, but instead of using the raw scores, I'm going to use the z-scores to show you how to find the proportion between two different z-scores. So 0, 1 standard deviation, 2 standard deviation, -1, -2 standard deviation. Draw the same curve over here. So to represent what the table will give you when you look at z equals -1, this is what the table is going to give you. And I'm going to do this in a different color. And let's go a little bit smaller. This is what the table is going to give you to the left of -1. And this is what the table will give you for +2. Problem is, neither one of these is what we're going to be asked to find in the problem. But we can use some subtraction here to help us out. If we subtract this section from the big proportion, we could actually find out exactly what we're looking for in this problem, which is this area right here. So if you find this proportion for z equals -1, and you find this proportion for z equals 2, and you subtract them, the difference will give you the proportion of the range. Okay, so z equals -1, let's find that proportion, then z equals 2, we'll copy them both down. So go back to table A. So z equals -1.00, that's going to be 0.1587. Let's copy that down in our notes real quick. This is 0.1587. 2.00, go to the positive side of the table, 0.9772, right there. This is 0.9772. Now if you subtract those two numbers, what you're going to get is 0.8185 as your proportion between z equals -1 and z equals 2. So your conclusion with our proper sentence in context, you're simply going to say about 81.85% of typists type between 45 and 90 words per minute. So again, this problem's different because they asked you for a range of z values, the proportion between those two, and the table's not set up directly to do that, but indirectly you find the two proportion and then subtract them to find the range of proportions. The next example. Suppose that the distribution of net typing rate in words per minute for an experienced typist can be approximated with a normal curve of 60 words per minute and a standard deviation of 50 words per minute. A company only considers hiring typists that fall in the top 10% of the distribution. What is the minimum words per minute a typist would have to maintain in order to be considered for hire? Now, they are not giving us the raw score for the z-score. They're actually asking for that raw score. What is that words per minute? And what they give us is the percentage or the proportion of the data, the top 10%. So let's draw a picture and show you what we're talking about here. So in our normal curve, we're not going to concern ourselves with z-scores and means here. I'm simply going to draw two sections. One for 10%, one for 90%. And these are just approximations. And what we care about is this section right here. I want to figure out exactly what's this z-score, and then from there, what's the x value or the typist score, words per minute. So we got to work backwards. Because not only does it not give you the z-score, but it gives you the proportion, but also we know that from our table, it gives us the left side of the curve. So what you're going to do is look for 90% on your table. What's closest to 90% or 0.9 on your table? Let's go back to our table. And you're in this entire set of numbers, look for 0.9. None of these numbers come close yet because this is the negative side, so up to 0.5 for 0. And look through here. I got 0.8849. You keep moving up. Okay, 0.8980, 0.8997. Okay, I found where it crosses over 0.9 between these two. If it falls in between two z-scores, just choose the one that's the closest. So between 0.8997 and 0.9015, 0.8997 is the closer one. So we're going to choose that one. Find the z-score. So it's the second to last column. So I scroll up here. 0.08, 1.2. So z is going to be 1.28. Let's go back to our notes. For this, we use 0.8997, which gives us a z-score of 1.28. Now, we got to work backwards to find the context. What is the z-score of 1.28? Because it doesn't answer the question in terms of words per minute. So your z-score formula, remember, is x minus mu divided by sigma. We know right now z, the mean, and standard deviation. We're looking for this x value. What is that words per minute? So plug in your numbers and solve for the appropriate missing value. 1.28 equals x minus 60 divided by 15. Multiply both sides by 15. Then you'll add 60. X is going to be 79.2 words per minute. Or in terms of the actual conclusion, you would say the minimum words per minute a typist would have to maintain to be in the top 10% is 79.2 words per minute. And that's it for the conclusion, as long as you refer back to the context of the problem. So, within these three examples, we did one of each type, you could say. The first one was the most basic one, most likely. It's just a simple area to the left of a curve. Find your x value, convert it to z, go to the table, find your proportion, and then answer with a sentence. The second example, we talked about how it's in between two z values. You had to subtract those proportions. The last one, you had to work backwards. You had to use the percentage to go to a proportion, to then find a z-score, then find a raw score, and then you answer with a sentence. So table A is going to be frequently used in the back of the book. In case you don't have your book, it's very easy to Google table A, or if you look at the title of the table, standard normal probabilities table, you'll have tons of examples to work from. It'll always be there for you.